Hello everybody and welcome to our Hooke's Law video. So this is our next force that we're going to be looking at in our dynamics unit. So this one is an elastic force and it abides by a law called Hooke's Law. So the first thing I want to talk about is what is an elastic force. So an elastic force is a force that works to return a distorted object to its equilibrium position or its rest position. Sometimes we refer to it as a rest position. So it's a force that works to return a distorted object to its equilibrium position. Some examples of this are elastics, obviously. So imagine you are stretching an elastic out. You can feel that the elastic actually wants to return back to its resting state, and it requires you to apply a force to stretch that. Springs work the same way. So whether you stretch a spring out or compress the spring, it wants to return to its original state. So if you're stretching a spring out, you can feel that it's pulling back and it wants to return. Or if you're compressing the spring, it's pushing back and it wants to return back to its resting state. This is how bouncy balls work. This is why they're so bouncy. Because when they hit the floor, they compress slightly and then they want to return back to their state. So they do that, and when they do that, they push harder on the floor than a normal ball would. Just that distortion. Trampolines work that way as well. Trampolines have elastic forces. So this is all governed by Hooke's law. So Hooke's law states that the amount of restoring force or elastic force might as well make it look somewhat pretty. Elastic force. So the amount of elastic force is proportional to the amount of distortion. Wow. So basically, the further you stretch that spring out, the higher the forces required to hold it there, because it's a larger spring force trying to restore it, if that makes sense. Springs are weird because they end up deforming, but if you had an elastic and like a really thick rubber band, like those workout resistance bands, the further you stretch those, the harder it is to keep stretching it, right? There's more force trying to return it back to its resting position. So the amount of elastic force gets bigger as the amount of distortion gets bigger, the amount that you're changing it. And this works on a formula like this. Force elastic is equal to K delta X. So let's talk about this a little bit. This is elastic force. And that is measured in newtons. K is the spring constant. So just like mu for friction, the spring constant is different for each type of material. So basically, it's how stiff the spring is. And this is in newtons per meter. So a really, really thick spring that's hard to compress or stretch would have a really, really high K value. But you know, those little springs in pens, they're just little tiny things and you can easily squish them and stretch them. They have a very low K value. And delta X is the distortion and that's from rest. It's measured from the resting position, and that is measured in meters. So I want to draw a picture and talk about this a little bit, what's actually happening. So say we have a spring, and it is regularly 10 centimeters. I'm going to reach in and grab that spring from this side here, and I'm going to pull it, and I'm going to stretch it. Let's say it's anchored to the wall. It's anchored to a wall. I'm going to stretch it out. So now, oops, my spring looks something like this. So now I'm applying a force, and I'm going to hold it there. So that's my applied force. If this here is my 10 centimeters, and I've stretched the spring out to be a total of 18 centimeters now. What's happening is, if I'm holding it there, that means there's no net force. There's no acceleration, no movement. That means that the force applied has to equal the, I'm going to put it up here so it doesn't cover my spring, the force elastic. So the applied force I have to apply is the same as the force, the elastic force. The K value is given to you, and the delta X, the distortion, isn't 18 centimeters. It is from rest, which was 10. It is this part right here. So delta X would be 8 centimeters. I've distorted it 8 centimeters. Resting length is 10. I've created a spring that's 18, or I've pulled it until it's 18 centimeters. That means my distortion is 18 centimeters. And you can see that your distortion moves in that direction, and your force elastic moves in the opposite direction. So sometimes you will see the force elastic formula written with a negative sign here to compensate for that. Again, negatives and positives are directional, so you don't have to use it. You just have to know that if you see it, or if it comes out as negative and something's going on, start thinking about the direction. Because again, if you had that same spring and I decided to push it in, so now I have my spring like that, and it's only now 6 centimeters. Originally it was 10 centimeters. That means I've pushed it 4 centimeters. That's my delta X. Now my force applied is this way, and the spring force is trying to move me this way. And you can see that the delta X and the force of elastic are in opposite directions, and that's what that negative compensates for. And actually, I'll look at your formula sheet right now. So there isn't a negative on that formula sheet, but sometimes you do see that negative, and I just want you to be aware of that. Okay, let's look at an example. A student stretches an elastic band with a spring constant of 50 newtons by 15 centimeters. How much force are they applying? So we know our spring constant is 50 newtons per meter. We know our delta X is 15 centimeters, and we are looking for the force. So in this case, it's the force they're applying, but if they're stretching the elastic band and they're holding it there, then force applied will equal force elastic. So now we know our formula is F is equal to K delta X. So we can plug everything in. The problem right now is that we have meters here and centimeters here. So we know that 15 centimeters is 0.15 meters. And now we want to use the 0.15 meters in our formula. So now we have 50 Newton meters, and we have 0.15 meters for our distortion, because the student stretches the elastic band by 15 centimeters means that we've distorted it 15 centimeters. We don't know the original length, but that's the amount of distortion. And now we can multiply that, and we get 7.5 newtons. If you look, meters over meters cancels, we're left with newtons. Example 2, Al McInnes. Hopefully some of you know who that is. He's a hockey player from, well, even a little bit before my time too. So you probably might not know. You probably don't know who he is, but he had the hardest slap shot in hockey for a lot of years. So it says here, Al McInnes uses a wooden hockey stick with a spring constant of 850 newtons per meter. So that means our K is 850 newtons per meter. What is the distortion on the stick? So we're looking for delta X if he exerts 525 newtons while taking a slap shot. So the formula we are going to use, F is equal to K delta X. We're looking for delta X, so we can divide both sides by K. We want to get delta X by itself. So now we have delta X is equal to force over K. And we know the force was 525 newtons. The K is 850 newtons per meter. And that is going to be 0.62 meters. So I don't know if any of you have seen like a slow motion picture of somebody doing a slap shot in hockey, but when they do that, their stick actually bends. So we know a hockey stick is usually straight, but when you do a slap shot, let's say the puck is here, the hockey stick, this is your stick, it's a terrible hockey stick, it actually ends up bending a little bit, and that's how they're able to shoot the puck that much. That's your hockey stick. So we get a bit of a bend from straight. That's straight. So how much did it bend? It bent 62 centimeters. And that's how, yeah, that's why the puck moves so fast when they shoot it. That's a terrible drawing. I play hockey, and that should be better. I feel like a bad Canadian. Just kidding. So hopefully that makes sense with elastic forces and Hooke's law. We will do more in class, and we're going to do a lab on this, which is really fun. But yeah, thanks for watching. Don't forget to like and subscribe.